All right, what's up, guys? I am going to go through as many of these as I can. I'm going to pull up Desmos Scientific Calculator so we can check that out and do our calculations there. Bear with me. I'm not going to write everything out. I want to do this really quickly. So let's do number one. How much energy in joules we produce if the sun converts 8 kilograms of mass into energy? Equals mc squared. We're just going to plug that in. Mass is 8 kilograms. C squared is, well, c squared. So 8 kilograms times 3 times 10 to the 8th raised to the 8th. And we want that squared as well. So we'll go ahead and square that and we get something. I'm going to be very careful because I've had some problems with this lately. Just want to make sure it's only squaring that number and then multiplying. So 7.2 times 10 to the 17th. 7.2 times 10 to the 17th is what we're looking at there. Pretty easy for that. 8 times the speed of light squared. I don't know what. Yeah, of course. 8 times the speed of light squared. Okay. Number two, a megaton nuclear weapon produces 4 times 10 to the 15th joules of energy. How much mass must vanish? So I'm doing the same thing. I just want to solve for mass this time. So it's going to be the energy here listed divided by c squared. So let's do that. So the energy listed there was 4 times 10 to the 15th. Let's put that in parentheses. 1.5. There we go. And divided by c squared. So we're going to do c in double parentheses here times 10 to the 8th. And then we'll put that parenthesis there, and then we'll square it, and then we'll put the other parenthesis on the outside, and we get 0.044. Great, 0.044. Energy divided by c squared should be the mass, 0.044 kilograms. Did I put everything in there? 10 times 10 to the 15th. C squared, 0.044. And that number does not show up. So let's double check what we're doing here. We got E equals mc squared. We want to find how much mass. 5 megaton. Oh, 1 megaton. So it's 5 times that energy. I'm sorry. So 5 times this. So let's do that in here. 5 times. So 1 megaton was that much energy. 5 megatons would be so much more, and at 0.22 kilograms. There we go. There's our answer. My bad. So 1 megaton, and they said they want to know when 5 megatons. So that's the mass right there. So 0.22 kilograms. A lot of energy, right, for such a small amount of mass. This is why nuclear power is so powerful. All right, next question. United States consumes about this much energy all year. How many years could we run the United States on energy released by a solar flare? So take the solar flare divided by the energy. That'll be how many years? So the solar flare was 10 to the 24th. That amount. Something ridiculous. Divided by... It was, what, 2.5 times 10 to the 19th? 2.5 times 10 raised to the 19th. Looks like 40,000. 40,000 years. 40,000 years based on the energy from one solar flare. Pretty incredible. I know I mentioned in class about how solar power is powerful. We'll get there. Oh, this one, let's try a different version. There's not a different version, but I'll walk through this with you. And I want to show you something with this one too, because some stuff makes me think that we don't, that maybe I didn't explain how to use all this stuff that's over here on the right-hand side. But if a granule center rises and given at the rate in the textbook, I got to find that, right? I got to find that rate, and then I just need to do it for 15 minutes. So let me find that. I'm going to search for granule. Let's see if that comes up with anything. When I search for granule, I get actually only one spot where that's mentioned in the book, in solar atmosphere. And actually, if you scroll down, it'll highlight the thing, so I can scroll pretty fast and it'll show me where that's at. So as I read here, granules can be several blah, blah, blah. Some other thing about granules. Centers, edges are hotter than the edges. We're getting close. Centers are rising and the edges are sinking at speeds of 0.4 kilometers per second. 0.4 kilometers per second right there in the yellow. So 0.4 kilometers per second, and my problem was, and we'll have to get back to it here. It may exit you out of it, but we'll come back to it. Nope, number 4. 0.4 kilometers per second for 15 minutes. All right, 0.4 kilometers per second for 15 minutes. Well, 15 minutes times 60 seconds per minute is 900 seconds. So 900 seconds times 0.4 per second. So 900 seconds times 0.4 kilometers per second. The seconds have canceled, left at 360 kilometers. So some of this information you got to look up what the book says. Googling it'll give you a range, because this is all of this is these are averages, right? And they're saying what the average is. So make sure we stick to our information. Some of the stuff like this question you might find online. Solar wind can gust as fast as the highest speeds listed in this chapter. This is another thing that we got to look up. I got to type in here, and I got to go solar wind. And when I search solar wind, I see solar wind here, some other stuff, a bunch of stuff with solar wind. So I'm just going to click on the first one. Escaping the corona, solar wind. And its solar wind can travel at velocities between 300 and 1,000 kilometers per second. So we have solar wind of 1,000 kilometers per second. There's my highest speed listed in the textbook. So that's the higher range, 1,000 kilometers per second. Let's go back to the question. Remember, I got to close out of it and re-go into the assignment. But 1,000 kilometers per second, how long does it take to reach Earth? Earth is how far away? Sun to Earth distance in kilometers. I think I spelled it wrong, but 149.6 million kilometers. And traveling 1,000 kilometers per second. So how many seconds is that going to be, and how many days? All right, let's go ahead and do this. So we got a 149.6 times 10 to the 6th. That's a million, right? 149.6 million. All right, divided by, whoops. Got to do the answer divided by. When you do it this way, it preserves this answer. So if I go up here and change this, all right, it changes my calculations all the way down through. So that's a cool feature of this calculator. Divided by, what do we say, 1,000 kilometers per second? It's going to be that many seconds. How many days is that? Well, a day is 24 hours, 60 seconds. So I want to know how many hours this is, and then we'll do 24 hours in a day. So there's 3,600 seconds. So I'm going to take that answer and divide it by 3,600. That's in 1 hour. So we're talking 41.5 hours, and I'll divide that by 24 hours, 1.73 days. Now you could do 60 and then 60 again to get this number if you wanted to, but I did it all together, 3,600 to convert seconds to hours. There's 3,600 seconds in 1 hour. 41.5 hours divided by 24 is 1.73 days. Boom, we're good there. Number 6 is the small angle formula. Again, I can do the search button. I know where it's at, but I'm just going to type it in here anyway. Small angle. Reasoning with numbers, small angle formula. Here it is. I need the, for that question, I needed something different. I got the angular diameter, linear distance, diameter over distance, and then this 2.06 times 10 to the 5th. I want to save this in a different piece. So what I'm going to do is, give me a second to organize this. All right, so first one says angular diameter of a star. That's what I'm going to find. So I'm going to start with that 2.066 times 10 to the... Okay, looking up the small angle formula we have right here on the side. I decided to get it here because I wanted to look at it back and forth. So we're solving for this piece up here. So I set that up and did the calculation, knowing that everything has to be in the same unit. So everything has to be in kilometers in order for us to get out, or at least in the right units. It could be light years as well, but I used kilometers here. So there was some, I had to look up some distances and stuff. But we've got the constant that's listed here, 2.06. All right, so we're solving for this. So it just means we have to multiply each side by the bottom term here. Linear distance over the linear diameter over distance. They said it's a star like the sun. The sun is 1.39 times 10 to the 6, 1.39 million kilometers from the across. That's the diameter of the sun. All I did to find that was just Google it. Diameter of the sun in kilometers. There we are. 1.39 million kilometers. And then light years, 5 light years is that many kilometers. And those are the two distances I have in there. Once you hit that, you get 0.006 arc seconds. So 0.006. And then is the Hubble Space Telescope able to detect in detail on the surface of such a star? This is a yes or a no question. So the resolution is 0.1, and this is smaller than 0.1. So the answer would be no. All right. Number 7, how much energy is produced when the sun converts 2 kilograms of hydrogen into helium? Hydrogen into helium. We have that one in there. I showed you where that was located before, the sun. And we can go to hydrogen fusion, and we look at the breakdown of that chain reaction. I think actually it's the math that was in this chapter. Yeah, here we go. Sorry. We get a difference of mass of 0.044, 6.69 to the whole. So part to whole, we have a ratio of 0.044 divided by 6.69, and we get this ratio, or that percentage, times 2 kilograms. Oops. That percentage, that answer, times 2 kilograms means this much mass is being converted. Of that 2 kilograms, this much, 0.013 kilograms, is being converted into energy. So I take that times c squared, which is 3 times 10 raised to the 8th. I'll go ahead and include that in there. I'll square that. And I get 1.183, or 1.18 times 10 to the 15th joules. So I'll put 1.18 times 10 raised to the 15th. Hopefully I didn't screw up the decimal places here. Yeah, I probably did. Or did I write the right number in? 1.1838. Let me see here. Get it different. Let me square this myself. Something was going on with this earlier. Oh, that might be why I had 2 of them in there. Let's do it like that. 1.8 times 10 to the 15th. Yep, that is the correct answer. So I don't know what's going on here. I was messing with this earlier. There was a problem. That is how you do it. I don't really know what else to do. I change it to 9 kilograms. The only thing I have to change is where I put 2 here. I need to change that to a 9. And that changes my answer to 5.3 times 10 to the 15th. So 5.3. Let's try that. Maybe it's because I put 2 decimal places and only once 1. I'm not sure. Sometimes these can be annoying to deal with. But it should be something related to that. 3.3 maybe? I don't know. Let's try another one. This says 4 kilograms. Once again, we're doing the 0.044. We're doing this ratio correctly. And we're doing the E equals mc squared correctly. I'm not really sure what the problem seems to be. I've done this a couple times now, and it works out well. I don't really know why it won't work out this time. So what was it? 4 kilograms, where answer should be 2.37. Let's try 2 decimal places this time. 2.37 times 10 raised to the 15th. Is that 15th power still? Yes. Still incorrect. I don't really know what's going on here, folks. I can try it one more time, but make sure I got the ratio right. Give me a second and I'll figure this out. All right, folks, I've tried this a couple more times and I'm getting mixed results. I'm trying a bunch of different ways. I get it right once and then I get it wrong a bunch of times. I'm doing the same thing each time. I'm not sure what's going on with this question. It's clearly a rounding error of some sort. I don't know if they want you to round this to 3 or 2.97. We'll try it this time, see if it works. But otherwise, I'm just going to comp this question for you guys as I grade this, remembering to do that. And I can't even type anything in anymore. Great. All right, 10 raised to the 15th. See what it says here. All right, that time it went through. I don't know what to tell you why it's doing that. I'm not sure. So do your best with that one. This one was just a conversion. So we're taking the number, the total amount released divided by how much was in each 4 times 10 to the 15th. So we'll do, what was it, 10 to the 26th, 10 raised to the 26th, there. I'm going to divide that by 4 times 10 to the 15th. So under here, do 4 times 10 raised to the 15th. No and no. Try that again. 2.5 times 10 to the 10th. That's for 1 megaton of, how many megatons of would that be equivalent to? So that's 4 times, oh my gosh, 2.5 times 10 to the 10th. 2.5 times 10 raised to the 10th megatons of TNT. That's a whole lot of TNT. And then, of course, the last question we know is the ratio is 1. So we're good there. All right, hopefully you can find what you need through all those questions. Use the search this course button as liberally as you need to find the information that you're looking for when doing these questions.